Okay, so there seem to be some questions on section 3.5, the rational function section dealing with graphing the rational function specifically. So I wanted to go ahead and do another example problem that you guys could reference. The problem that we're going to take a look at is going to be the rational function y is equal to 3x squared minus 12 all over x squared. So we're going to go ahead and take a look at how to actually set this up. I'm going to do my best to draw this freehand. So we're going to have an axis, an x and y axis. And it's pretty straight. Okay. So we're going to do this in shifts. So the first thing that we're going to do is we'll take a look for vertical asymptotes. Okay. So in order to find vertical asymptotes, this is where we focus on the denominator. And essentially what we're doing here is we're looking for restrictions. So I'm going to just look at this x squared. And what I don't want to happen is a situation where the x squared would equal 0. And this one's actually pretty straightforward. You probably can do this one just by looking at it. But if you do this algebraically, we would square both sides, or take the square root of both sides. And as we noted, the square root and the square will cancel each other out because they're inverses of each other. And this just leaves us with a solution of x is equal to 0. So I'm going to note our vertical asymptote actually rests right on top of the y-axis because this is where all of our x values are equal to 0. Okay, so it's a little bit hard to see, but I drew a dotted line in orange right on top of the y-axis, or the x is equal to 0 line. They're one and the same. The next thing that we're going to take a look at would be the horizontal asymptotes. Okay, and please refer to your book if you need to, or your notes, where we have 3 different cases. Okay, so we have one instance where the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, which in that case would mean that we have a horizontal asymptote at y is equal to 0. And in this case we don't, because the degree for each polynomial is 2. Okay, so our second case then would be if the degrees of the polynomials in the numerator and the denominator are equal, then we would go ahead and do a ratio of the leading coefficients for your degree. So in this case, we would have y is equal to a 3 because our leading coefficient here would be, let's see here, 3x squared. So our leading coefficient is 3. And then our leading coefficient for our x squared would be a 1. So this just simplifies down to 3. So I will go ahead and note this one in pink. So 1, 2, 3. I have a horizontal asymptote that's here. So note that I'm putting these asymptotes as dotted lines because technically we don't see these values. If you were to graph them, at least for this particular problem, you wouldn't see them on your screen, mostly because of the pixelation. But in a formal graph, if you're doing it by hand, I should just see these as dotted lines. They aren't actual physically solid lines. Okay, once you find your vertical and horizontal asymptote, we're going to go ahead and look for x-intercepts next. Okay, so when we are looking for x-intercepts, our main focus is going to be on our numerator. The reason being is if x-intercepts are all of our y values are equal to 0. So we would set this function equal to 0. And if you notice, what I can do is I can make this look like a proportion, which then allows me to do some cross multiplication. Okay, so 0 times x squared would just be 0, and 1 times this quantity of 3x squared minus 12 gives me 3x squared minus 12. Okay, so from here, what I can note is I can pull out a factor of 3, and that gives me x squared minus 4. Okay, and then from there, I see that I have a difference of squares. So I can factor this as x minus 2 and x plus 2. Okay, and from here, if I have 3 times this mystery number times this mystery number, and I know that the final product is equal to 0, then what I can kind of guess is, or maybe hypothesize, is that either x minus 2 is equal to 0 or x plus 2 is equal to 0. And suddenly this takes us back to a very simple situation here. I can solve for x minus 2 equals 0 as well as x plus 2 is equal to 0. So I'll add 2 to both sides in this case, and this gives me x is equal to 2. So that means I have an x-intercept at 2, 0. And then with this one, I would subtract both sides with a 2, and that would give me x is equal to negative 2. So that means that I have another x-intercept at negative 2, 0. So I'll go ahead and plot those. Okay. So technically what you should be doing now is you should be looking for y-intercepts. Okay. So note in this case, if you have y-intercepts, that's where your x values will be equal to 0. Okay, but you should notice that there's something inherently wrong here. And I'll go ahead and highlight that in the orange. I have a 0 squared in the denominator, and you should be kind of catching this and kind of saying, well, 0 squared is 0. I can't have 0 in the denominator. And we actually noted that already when we looked at our vertical asymptote. So in this case, we won't have any y-intercepts for this problem. Okay, so from here, what you can do is you can do some sign analysis if you feel the need to. If not, you can go ahead and kind of take a look at what you have in your graph. Note that asymptotes kind of act like an invisible fence. Technically, you should not be able to cross them, especially the vertical asymptotes. So, but they do get close. So in this case, I'm coming through, I will hit my intercept because that is a point, and then it's going to get close to that vertical asymptote at x is equal to 0. And we'll see the same thing here. I'm relatively close to the horizontal asymptote here. I touch and cross the x-intercept, and then it goes down, again, getting ever so closer to our vertical asymptote. This is our final solution. So here's our answer. Okay. If you have any other questions, I encourage you to either reach out to a tutor or come see me. And that's it.